Bismillahirrahmanirrahim. Hello students, welcome to the electrical engineering channel. In this lecture, I am going to discuss the magnetic field intensity due to a solenoid. So solenoid is actually a magnetic device which is established by making turns over a ferromagnetic material. So any core or any ferromagnetic material which is cylindrical in shape, and if we have windings over that cylindrical shaped magnetic material, that constitutes a solenoid. So we have two types of solenoids. In the first type of solenoid, we have infinite number of turns, and in that case there are actually infinite current elements or current filaments which are carrying conductor, and the direction of the current is in the phi direction, as you can see in this figure. So this is an infinite turn solenoid, and this is a finite turn solenoid, and in this case we have n number of turns which are done over this cylindrical magnetic material, and this is a solenoid which is having n turns, and we can say these are finite number of turns, and the length of the solenoid in both cases is equal to d, and the current flowing is equal to I in this case. But in this case, since we have assumed infinite number of turns, so the current flowing through the turns can be assumed as the surface current, right? So this is the surface current, and the surface current is equal to K, and K is equal to Ka times A phi. A phi is the unit vector because the current is flowing in the phi direction, and the total current can be evaluated by multiplying this current density with this cylinder length d, because the current is distributed across the length of the solenoid and the length is equal to d, so I will be equal to K into d, right? And the radius of this solenoid is equal to A. So let's start the calculations. For continuous or infinite solenoid, the Ampere's law can be applied, and H dot dl will be equal to dl is equal to dz right? So this is dl, and the length of the solenoid is equal to d, so it will become h into d az, right? So h dot az will be equal to hz, component of h along z, and that is equal to the current enclosed, and hz into d is equal to current enclosed, and current enclosed is equal to current density multiplied by d. So it means hz is equal to ka, or h is equal to kaaz, right? Because h has only the z component, so h is equal to kaaz inside the solenoid, and h is equal to 0 outside the solenoid. So for the solenoid with n turns, we can draw such a figure, and we have to apply this Ampere's law for the closed path, and closed path can be made as A to B, B to C, C to D, and D to A. And this is the n-turn solenoid, and we can see there are n current elements in n number of turns, right? If we have n number of turns, then there will be n current elements. So this is first current element I, this is another I, this is another I. So if we have n turns, there will be uh, the total current of n times I. So n into I will be the total current in this case. So let's apply the Ampere's law. So H dot dl is equal to H dot dl from A to B, B to C, C to D, and D to A. For the branches B to C and D to A, H dot dl, H and dl will be at 90 degrees because the magnetic field intensity is in this direction around the coil, and these two uh, sections will be lying perpendicular to the direction of magnetic field. So H and dl will be at 90 degrees, so the dot product will be equal to 0. And for this section C to D, the magnetic field intensity is equal to 0, right? Magnetic field intensity is only available inside these terms. So for this region C to D, this integral is again equal to 0, and for this section from A to B, we can evaluate the Ampere's law, so that will be equal to H into D, and H is equal to 0 outside, and that will be equal to n times I, because there are n current elements, and the current in one element is equal to I, and current in all the elements will be equal to N times I. So H will be equal to Ni divided by D, and this is the unit vector Az. So the direction of the magnetic field intensity will be along the z-axis. Now the question is that why the magnetic field intensity is zero outside the solenoid? The reason is that the current is flowing in the circular direction. So it means outside the solenoid, we have to consider the total current or the net current. So outside the solenoid, we have to make another surface, and within that surface, the net current is equal to zero, because at the upper side of the solenoid, the current is flowing in this direction, and for the lower side of the solenoid, the current will be flowing in this direction. Because the current is flowing in the circular direction, so the net current will be equal to zero, because same current is flowing in this direction and same current will be flowing in the opposite direction. So the net current will be equal to zero. So that's why the magnetic field intensity outside the solenoid is equal to zero. And that's what we also observed for this coaxial cable. But in coaxial cable, the current was flowing along the length of the cable. But in this case, the current is flowing along the phi axis. So that is all about our derivations of magnetic field intensity for two types of solenoids. And I hope you have understood how the mathematical forms of these magnetic field intensities are derived using Ampere's law for both solenoid types. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.